Welcome to Texas. They say everything's bigger in Texas, so we thought we'd build the world's biggest backplane at 56 gigabits per second. Hello, my name's Ralph Page. I am an active systems architect for Samtec. We are going to show you today how we used our TwinX cable to make a 5-meter backplane. You are already familiar with using our TwinX cable to get across the board, where copper losses, no matter what laminate you use, what stack-up you use, simply prevent you from going the many inches across a board. You're familiar with using a Samtec TwinX cable from going from a chip all the way to the front panel, and you're already familiar with using Samtec TwinX cable to go from one board to another board, a flexible backplane if you will. But how about if you can go from one rack to another rack? That would mean a cable 3, 4, maybe even 5 meters long. So we built a cable 5 meters long, equipped it with 40 pairs of TwinX, running at 56 gigabits per second. That'd be over 2 terabits per second, or like 400 gig Ethernet sets. That's a lot of data. So the question is, can we do it? Well, we could build a cable. We built a cable and we're showing it today. Question is now, does it work?
I'm Tim Horrell from eSilicon, and we've brought our 56 gig SerDes that's built in TSMC's N7 process that's now available for licensing to drive this 5-meter cable.
So let's show you what's going on with this demonstration. Here is an XMX connector. We've got it connected via a paddle card to the silicon. This cable, as you can see, is really long. That's 5 meters. You can see it's about the same as my index finger in terms of diameter or circumference. And 40 pairs in here, each running at 56 gigabits per second cable.
So on the electrical side of the demonstration, I wanted to point out that full path length is a total insertion loss of minus 38 dB. Only 21 dB of which is the cable itself. The remainder is all of the supporting elements for our evaluation board and the paddle card interconnect. To start up the demonstration, our user interface is very easy to launch. We start a new kernel and begin the initialization process. To take this further, I'll now turn this over to Roberto from our Pavia, Italy office.
Here we are. Thank you, Tim, for the introduction. We are just few clicks away from seeing the real performances of these SerDes on the field, or in this case, on the floor. So what we can do is just to show how simple to control the transmitter on one of the 4 lanes that are part of this SerDes IP is going to be. So we just click the transmit. We will select the lane 3, that is the one that is hooked to the sampling scope, and selecting PRBS 13 as the standard prescribes, we'll be able to turn the signal on. And in just a second, we will see how it behaves real time on the sampling scope. We designed the user interface keeping an eye on the simplicity. We wanted to be as user-friendly as the integration of the entire EP will be in the real life. The interface is also plenty of other features. We will now show how simple it is to turn on another lane that is injecting the data through this long cable and configuring the analog front end on the other end to receive the data and do the pre-emphasis that is necessary to reach SNR performances that will allow us to operate almost error-free without FEC, and for sure with error-free operation after FEC. So let's do that together. So we just go into the lane number 2, we will turn that on, and we will then get into the RX control, and we will configure the CTLE, and we will power it on. That's done. The data lane is up and running, and we will be able now to look together at the performances of these 56 gigabit PAM4 SerDes on this 38 dB insertion loss channel. So one thing that we can do at first is to look at the DSP. This is a fully digital SerDes IP, and all the performances after the analog interface is recovered through a pretty long FFE and a DFE. And we're going to look at the data real time now. So if we open the equalization monitor, we will be able to look at the FFE taps and the DTL taps real time. We can see that even though we have a pretty high insertion loss, we can reach more than 50 dB of SNR. This SNR translates into FEC error-free operation. We can look that through the bit error rate monitors that is running real time, doing an acquisition, and after a little bit of processing, we see that we have an error rate. Oh, here we are, 0 errors. How lucky we are. Just do another run. 0 errors again. I don't want to keep you busy for many hours without any errors. So we can do another thing that is always requested, to have a nice eye. So we can start the acquisition of a real-time eye diagram and look at that together. And we can even make it bigger. And there's also pulse response and many other features in this user interface that has been really thought to be as easy as possible, but at the same time to give the opportunity to be fully controllable, even for advanced users, being a wrapper around a command line interface that will allow the final user to do whatever test they want. So others to come, just come to the booth and see us.